Okay, our next talk is by Mורין, בשם גנב to brainstorm over Israel desert and excessive flooding potential.
Okay, good morning. I'm happy to be talking this happy occasion, the occasion to Aaron. I will talk about the shape and the dynamics of desert rainstorm and how it's connected with flash floods in the desert area. The work is done by many of the lab group members. Some of them are here. It, Bar, some already finished. Alone, Nadal, Francesco. And I will start with Aaron paper from 2004, where he presents here the distributions of durations of rain showers that occur over this research area, and claims and talks about how important the durations of these rain showers for runoff production and for and actually most of the showers are too short to be able to make a continuous flow over history. And that demonstrates the very important properties of the temporal variation of the rainfall. In my research and the group research, we were very interested to look at this topic, but in more, let's say, maybe larger scale, and also very interested in the spatial pattern, not only the temporal pattern that you can see here. And the best data to do such analysis is the weather data that provide, you can get from it really high resolution rainfall information in the order of kilometer and minutes, and most of the runoff productions in the desert area is from convective rain cells or the convective high rain intensities that you can see here in this radar image from May 2007. This, by the way, produced a huge flash flood in the Iran catchments in northern Dead Sea. And these small cores of rain intensity, you can see it here, are only a few kilometers aside. And we, so the name is the convective rain cell, and we're really were interested to study the properties of these convective rain cells and understand how they are related to flash floods in the desert area. So we wanted to do analysis of the climatology of these rain cells, really to learn to produce probability distributions of the space-time pattern of these rain cells. We know climatology usually is based on rain gauges, so you can have rain intensity or rain depth, but we want to look on space-time patterns in the climatology of this. To understand how these properties depends on governing the factors such as the synoptical system as the main governing factors, to see how they are this property change in space and time and what is the main controls, and to understand the relations with flash floods and the magnitude of flash floods. The methodology is, as I said, this is based on radar rainfall, so it's required a lot of work to first produce what we call the QP, the quantity precipitation estimation, to have a good radar rainfall data, well calibrated. Then we identify the convective rain cells, as you see here. We fit an ellipsoid to the core to track these rain cells in time, to have both space and time properties. And we can produce, if you do it for long-term record, you can produce probability distributions of the properties of, for example, here is the cell area, and the direction and speed of the rain cells. And this information, then to understand the hydrological implication, you can further input this information into hydrological model and to simulate and to look at the details of what is the relation between the properties of the rain cell and the catchment properties, of course, and the magnitude of flash flood. So this is very shortly the tools we used here. I want to start just to demonstrate with a case study analysis that it's already from 2014, sorry. This is in a case study, December 93, over the Becca catchment near Be'er Sheva, on 100 square kilometer. This was a very large flash flood. You can see the radar rainfall map over the catchment. This is the outlet, and there is high rain depth. This is the observed hydrograph. And if we put this over the regional envelope curve, okay, this is a unit peak discharge. So this is the units are 1 square kilometer. Sorry, and this is the catchment size. So this is the peak discharge from this event. And we wanted to analyze this to understand what is the relation between the space-time property of the vessel and the flash flood magnitude. So we decompose the storm into the convective rain cells. There are 56 rain cells in this event, and you can see the properties, the maximum rain intensity, the cell area, which the mean is about the size catchment, size of the catchment, lifetime about 30 minutes, and velocity about 7 meters per second. But when we analyze all these cells, actually using it as a logical model, we use this as an input in hydrological modeling. Actually, we found there was only one cell here that was the dominant cell and that was responsible for the large flash floods that occurred. Actually, 55 cells, even more, if they were not there, this was really still a very large flash flood. And if this single cell was not in place, there was no flash flood at all. So there is one dominant cell, and this is very typical to desert storms. There is many times only one major or flooding convective cell that produces the flood, and this was the properties of this specific cell. And now we can use like sensitivity analysis to see what is the most important properties of this cell. And we, again, with a logical model, we change the starting location of the cell. This is the peak discharge that we could get by this cell from different locations, the direction of the cell, and the peak discharge that we could observe, and the speed of the cell, and the velocity of the cell. And as it goes slower, the peak discharge is much higher. And in general, we could, what we got that just by changing location, direction, and speed. Okay, no rain, we didn't change rain intensity, just location, direction, and speed. The simulated peak discharge could grow more than 3 times from the original peak discharge. So these very important properties of the cell: the starting location, the direction, and the speed. So this is the original cell configuration, and this is what maximizes it. And what does it mean in terms of the envelope curve that we saw before? So this was the original peak discharge, and actually, by getting to this, to the maximum, if we look what makes this the highest peak discharge, we see this peak discharge move towards the envelope curve. It does not, of course, go over it, but it's getting closer. So this is one event, but this just demonstrates how important these properties. And now we want to dig in more long-term analysis or climatological analysis. Okay, so what are the possible speeds, direction, and properties of rainfall? And here, this is the master thesis of Edith, but I don't know if she's here. I did. This is her master's. She's going to finish soon, and the paper was just submitted. And Edith did actually hydroclimatological analysis of convective rainfall over the Dead Sea. You see here the study region, and when I talk about flash floods, these two catchments are going to be tiny cells all over this area. So we had 24 years of rather well-calibrated radar rainfall, divided into more than 400 rain events, and more than 10,000 convective rain cells from this analysis. So on average, taking everything, looking on the average rain cell, convective rain cells, it's about 90 square kilometer in size. It moved 13 meters per second from west to east, and the lifetime is less than 20 minutes. Okay, this is important to understand what type of catchments and what size of catchments can be most effective in flashlight producing from this cell. But this I do not take what today. Now, we divided the rain event into synoptical system using cluster analysis. She identified three major systems. Two are Mediterranean systems. One is Cyprus low, and the second is low, which is the east. The low is penetrate from the east Mediterranean Sea, but located eastern to the study region. And the active red sea troughs that we know very well in the desert region of Israel. You see, this actually is the most frequent systems that produce rain all over the study region in this analysis. You can see here this rose shows the direction of the storms, of the cells, and the speed. This is the speed. So, of course, the western component is the most can see very clearly. We see that the active red sea trough is bimodal. There's some northern and southern component, and the longitude is a bit northwestern component. And few of the properties we have many more shown as box plot. So the two blue and cyan are the two Mediterranean systems. You can see that in general they have shorter, longer duration, a larger cell area, but the rain intensity is on average lower than the active red sea trough, and the time of the individual cell is shorter. The active red sea trough has a shorter duration, small cells, and the intensity is higher, which is quite interesting. It's not surprising. We can expect it, but it's interesting to show it in the methodological sense. Now, we also wanted to see how it changed from north to south. Taking this gradient here, we know the rainfall. We have much more rainfall in the northern part of the Dead Sea than in the south. This is average over the longitude. Okay, so this is the mean annual rainfall. And the two main factors that plays here is the elevation. This is the topography. The maximum topography is that it's higher in the north, and also the distance from the sea is shorter in the north. So just showing you the main change without getting into the details. If we looking at the number of rain cells and cells area of the two Mediterranean systems, the cells of the Mediterranean system, we see that the cells in the north are larger, and there are more and they are larger. There are more cells and they are larger in the north than in the south. And this can explain the larger rain amounts in the north. But in terms of rain intensity, actually, the rain intensity is higher in the south than in the north. So again, the area with less rainfall, the intensities are higher. The active red sea trough shows also more cells in the north, but the area is larger in the south, and there is cannot distinguish a specific trend in terms of rain intensity for the active red sea trough. And in terms of flash floods now, so now this analysis is for these two catchments that are going to go here in the northern Dead Sea. From all events that produces rainfall over this area, 144 events did not produce flashcards, and about 30 did produce flashcards. And this is the difference between the sales property produced or did not produce flashcards. Not very surprising, but again, it's nice to see sales producing flashcards are larger on average, they are longer duration, and they are slower. Because again, the speed is really, really important. Properties of the store, of the cells, they need to be, they are slower, and we see it again. And the rate density is somewhat higher than those that did not produce cells. And if we look about the direction and speed, this is the flashcard producing events have some north-western components that is missing here. And again, the speed is much slower. And if we take only the large flashcard producing storm, from the flashcard only those produce the largest flashcards, we get very strong this component here. And again, the mean velocity is less than 10 meters per second, and it's very important. This mean direction is more or less the direction of the main axis of the catchment. So storms going from upstream, downstream, slowly. This direction has the largest potential to produce flashcards in this catchment. Now, okay, this is let's say a statistical look on these properties. We want, of course, to take it to better understand maybe the relation with flashcards. We mainly focus on two concepts. One is storm flooding potential. This is the largest flashcard a given storm can generate. And the probable maximum flood, the largest flashcard can occur in a given catchment. We're going to use this climatology now that we understand more what is the distribution of properties that is possible in the region in two stochastic tools. One is we take a real storm that already occurred and we have this database, but we can start change the properties of direction, location, and velocity. This is Barbara's master that she's now working on this, and we can check what is the impact on floods. And a weather generator, this is completely, produces completely synthetic storms. Again, but from this climatology, we have Nadav Peleg developed one for the northern Israel. We're going to apply to this area, but it still needs to be done. I just want to show one result from Bar master thesis. It's still under process. So Bar took the May 2001 storm. Maybe some of you remember it's produced very large flashcard in our boat catchment and actually ruined the stations, the hydrometric stations there. So we produce about 400 cubic meters per second in our boat. In Rachav catchment, it produces about 70 cubic meters per second event. What is the potential of this storm if you change this, again, location, direction, and speed? This is the envelope curve, unit. Now, if you take all these considerations of location, direction, and speed, this is the original discharge in Rachav, but you know you can get as high as the envelope curve for this event of a Rachav if you change it, change these properties, and the same for our boat. This is the original discharge, but all these values can get and up to the envelope curve. And it's interesting that it's still limited by the envelope curve. So we still preliminary, it's under study, and of course what we are interested is to understand what is the limiting factor except the size, catchment size is very clear, you can see here, but what are the more limiting factors? And we, of course, there's a lot to be done. It's under study, so in summary, so space-time patterns of convective rain cells affect flashcard magnitude. We show case study. We derive the climatology of convective rain cell of the Dead Sea, and we show the effect of the synoptical system and the north-south variation. The flashcard producing storms are larger, longer duration, and slower, and more intense. And again, the direction is related to the catchment main axis. We analyze now the flooding potential of the stone. This is still under study, and we show this limiting factor of the envelope curve. Still a lot to be done, but this is the results so far. Thanks.
One question? Yeah, go.
Your result that the average intensity of the storm diminished as you went to drier and drier areas surprised me because I was not less latency for intensifying the storm. So what's the mechanism?
This is something we really want to understand. But first of all, I can say that we see from different, we have a lot of evidence for this behavior. Not just for this analysis, also for simple gauge-based analysis. You can see that, let's say, if you take a given quantile of intensity, you see it much higher in the more dry areas than in the wet area, and it's really interesting. Now, what is the mechanism from a meteorological point of view? This is something that we want to understand, but it needs more research. But it's probably true because we see it from different directions. And this is why also flash floods, the magnitude of flash floods in the desert area will be always forgive. The envelope curve of the desert is higher than the envelope curve of the more Mediterranean.
Sorry, it was something simple about physics I didn't understand.
No, I think it's not trivial at all to understand why. Studies.
Okay, and we're going now to the last talk before the coffee break. Talking by John.